Okay, so we'll do the chapter 10, and then we go to chapter 11 bit here to say. So the chapter 10 we discussed the relative hyperbolicity and the strict convexity here. So 10.1. So we do the some ending and length to the end, and then so we remove some open set to make R into some boundary components here. So we will try to preserve the strict convexity. So we start with some strictly convex, relatively strictly convex projective structures, and then we show the relative hyperbolicity. So we show that the strict convexity implies the relative hyperbolicity, and then we prove the converse here in the 10.3.4. Okay. So this was first done by some Kupolong and Tillman crampon kits, but their strictly convexity is the real strictly convexity, and so it's not the relative version I'm using. So I'm using the generalized version. Okay, and so we need the two conditions like NA and IE, so which we'll explain later, and so So first of all, we will modify the TN. So we have TNs and it has a lens shaped TNs, and you can add these lens and it will still be properly convex and has a strictly convex boundary component with respect to for this component. And also, if it's strictly convex and E tilde is hyperbolic, and the hyperbolic end, I mean that it has a word hyperbolic and fundamental group, then the L union E will still have a more one more boundary component and one less T and okay, and strictness will be preserved. Okay, so the basically this is just to look at the how the end is added here and outside and inside. Okay, and so here I am proving that the convexity being preserved. So this second one, so L of course has a strictly convex boundary at both sides. So first one is no problem. And for the second one, so we have some totally geodesic boundary component, and there is AS hyperplane. Then so we have these two properly convex open domain from one side, and then another side here, which are invariant the pi 1 of E, and then you can take the union, and these will be again have a properly convex, and it will have a unique asymptotic hyperplanes. Okay. So the basic proof of that is that if you construct these domains, then these AS hyperspaces are determined by some these are uniquely determined by the fundamental group polynomial and these how they meet at Sn infinity. So that's how we can show these are corresponding to each other. Okay. And then so now we go to proving this theorem here, and so this theorem, of course, so of course the L as the first part is easy, but the second part is if always strictly SVC, and then it's relatively hyperbolic. It's hyperbolic, then any segment is in this boundary or in non-C1 points in here is in the closure of the N neighborhood. So these cannot contain any segment or non-sigma point unless they're at this boundary here. But but these are also strictly convex by our theorems. Okay, so we show that these are hyperbolic. But because these are correspond to closed hyperbolic, I mean closed convex zero projective manifolds with the hyperbolic fundamental group. Okay, so that's right. So that's how we show this. The, uh, so in the corollary is that if you have a lens, CA lens, the total geodesic hyperspace E, then each has a unique supporting hyperplane at L, and then L has a CA lens, and this has unique hyperbolic supporting hyperplane at L. Okay. Okay, so the for the RNs, if you have some RNs, then you can so these are lens cone shaped. So we can remove some concave affine neighborhood to show that these are again strictly. Uh, we can also get smooth boundary. So if it's strictly SPC, then you can remove these, and then you will still be strictly SPC. Okay, so strictness is preserved under this operation. So again, those are some arguments using the geometry of these lens cones. So we have to look at these, and then only thing that can go wrong is actually at the boundary of L, which is a lambda set. And then again, if this is a hyperbolic fundamental group, then it cannot contain any straight lines or straight segments in here. So that's the basic idea. And then of course C1 is you can do by the other arguments here. Okay. So we will go to proving the main theorem here. So we recall the Hilbert metric, and the Hilbert metric is denoted like this. And if it's so first thing is that if you have a properly convex domain and P is a subspace meeting the interior, and then if you have any point here, then there's at least a shortest path from X to P that is a line segment. Of course, it could be a path, some broken path, but the line segment does realize some shortest path, and so sort of shortest path from X have endpoints in compact convex subset of this set, and any line M prime containing M and the Y in M prime, then actually so if you take the shortest segment and then you take a subsegment to this point, then it's still the shortest segment. Okay, and or the bigger segment, some other point in there, and this is bigger. And if it's P is a complete geodesic case, then this will be always strictly increasing or strictly decreasing. So it will be a convex function. Okay. Sorry. So convexity, I didn't really prove it, but anyway, so I just go ahead to prove it. So this distance function actually is a proper function. You can easily prove that. So on this P intersect omega, it's a proper function, and so you just need to consider two-dimensional subspace Q containing gamma and X. So if gamma is any geodesic in here in X0, passing this X0 is some point meeting the M with the L here. Okay. Then you can go to two-dimensional cases, and there you prove that it is actually bounded compact set subsegment there, and then you can consider all the geodesic passing through it, and then of course these will be connected compact set. Okay, so you change these omega for each P, and then you can show these are compact connexes set. Also, you can show that this set is compact because you can always take any 2 points in it and then argue as in here. Okay. Okay. So then the next one is again very similar to here, containing. Just need to look at two-dimensional examples and so for again this is also done for just two-dimensional case here. That's enough to prove this. So these endpoints are called the foot of the perpendicular from x to gamma. So in this case, of course, the foot is not unique, not differently from the classical geometry. Okay, so the strict SP structure in the group action, so omega be a strongly tamed strict convex set, and then E be an N. If it's horospherical N, then so P be a horospherical PN neighborhood with P vertex, then there's a homeomorphism from this boundary of B minus P to this boundary of or tilde minus P, sending any point here to the endpoint of maximal point containing it. So there's homeomorphism. And if it's a lens case, again, you take the lens shape and neighborhood, and you can also get the homeomorphism as long as you remove this CU. And so these are of course commute with any this map will commute with action of this fundamental group, and so the basically this is well defined, and then you need to show these are onto, and these are just the geometrical argument that you can do. Okay, so for strictly SP3 structure, general lens are always lens by this corollary because the strictness will not allow any true generalized lens to appear because we can always connect up the lens here. Okay, and so if he always a strongly tame SP structure with lens, so you don't need general lens, just lens shape, horospherical, and then the P is an infinite order element, and every fixed point satisfies this condition. X is in the closure of a P and neighborhood is a concave end neighborhood of Rn, or the closure of ideal boundary component of Tp, or the fixed point of a horospherical end. Okay. So these are just the fact that you need to work with these BB and then how the strongest eigenvalue will work with these, and then you take the limit, and so any fixed point. Um, so uh, right. So so basically the because of this the holonomic closure has to be in the lens cone. In the lens case, the sigma cannot contain the other endpoints, so that's the thing. And so these are again using the strong the middle eigenvalue condition that the fixed points are always in here. Uh, and and the horospherical case is again very similar. You need to work with that kind of thing. Okay, and so again, for these strongly tamed strict SPs orbifold, then so for any infinite order element, it fixes exactly 2 points, which is or and it's partially proximal, or it is fixes some is in some fundamental group of n, and then it fixes some point in the concave P neighborhood or ideal boundary point or horospherical P and vertex. Okay. So so again so the thing is that if you have any fixed point in the horospherical P vertex, then you need to show that it is actually in the fundamental group of this PN fundamental group because these you have some invariance property. So if you have something intersecting, then they have to be in the group. And so for concave and neighbor, you get again they have some invariance property, so you can also show that it's true. And then for total geodesic, you can do the similar things. So so now it's not in any fundamental group, then it doesn't fix any sort of type of fixed points. And so this will fix some point X in the closure. I mean, of course, by the Brauer fixed point theorem, and so it's not in the and closure of any P-n neighborhood. So also it's X is a C1 point by the strict convexity. So I mean the strict convexity implies that these points outside these are C1. So it has some largest eigenvalue bigger than one and smaller than one. So of course this is infinite order means it has this property, and so if it's not positive real, then of course you can act by these to show it's not properly convex. So the largest norm eigenvalue is positive. So the attracting and the repelling fixed points, you can obtain these, and so of course there's at least two fixed points, and then um, so if it has a unique fixed point, okay, so then so it cannot have so norm bigger than one, smaller than one. So it has only one unit eigenvalue. So eigenvalue what just unit norm. So but lemma shows that there is a some sequence of cross curve where the Hilbert x goes 0. So it must be in the end neighbor. So this is observed. So the any element here must have at least two eigenvalues, two norms of eigenvalue, and must fix two points. And this has to be positive real eigenvalues because of this argument. And so um, so the no so then so then you show that any other fixed point, there cannot be any other fixed point in the boundary. And so the thing is if you look at the subspace spanned by these, and then if these or line segments from connect to A must be in this boundary, because if not, then you can sort of keep acting by G element to get a contradiction, okay, and not violate the proper convexity. So therefore, there need just two eigenvalue with the largest and smallest eigenvalue. Okay, and of course I mean this has to have a multiplicity one, because if not, then uh, then there is some so these are C1 points. So and then there's no straight segment containing it. So you can show contradiction from there. Okay. Yeah. Okay. So that part is might be missing here. Okay. Anyway, so you just need to show that part again. So additional argument. So then next proposition is that so for each for the R and Tn, so if you remove K, this one, or the total geodesic or the whole spherical point, so this is always going to be compact orbifold, and that's because you can always get a homeomorphism from here to the so for the lens type or whole spherical type, you already showed this homeomorphism, and for the lens type T, and you can always for the T, and you have to use some duality argument to get these things. Okay, so you have to take the dual and so on. Okay.